So our second review topic is 8.2 on polynomials, perhaps the most fundamental expressions or functions in mathematics. And before we talk about polynomials, let me just get into exponentiation real quickly. So what does 3 times 5 mean? Well, depending on how you interpret this, I'm going to interpret it as one way. 3 times 5 means add 5 to itself 3 times. Right? You could also think of it as meaning add 3 to itself 5 times, but I'm going to interpret it this way. 3 times 5 means add 5 to itself 3 times. So 5 plus 5 plus 5. And in this sense, multiplication is really just shorthand for repeated addition. Right? That's all multiplication means. If I said 7 times 5, that would be add 5 to itself 7 times. So multiplication, we don't need to write this down. We've said it. So multiplication is shorthand for repeated addition. What about 5 cubed? Well, that means multiply 5 by itself 3 times. Alright, so this is what exponentiation does. It's repeated multiplication. It's shorthand for multiply 5 by itself 3 times. It's in the same way as multiplication is shorthand for repeated addition, exponentiation is shorthand for repeated multiplication, is what I'm trying to get at here. And we'll formally define this. So b to the n, where b is just a real number, any real number, and n, we'll talk about more complicated exponents later in the class or later in the semester, but for now I just want n to be a natural number. So 1, 2, 3, 4, 5, and so on. But the formal definition of this is, well, b to the n means multiply b by itself n times. So this would be b times b times b times b times b n times. So n terms here. A little bit more terminology. B is usually called the base, and n is, of course, I've said this word a few times, this is the exponent. And because we want to work with actually a little bit more than just natural numbers here, there's one number that's not included in the naturals, which is 0. I want to be able to talk about b to the 0, so we'll just make this definition now. B to the 0 is always defined to be 1. Okay, so this is our definition of exponentiation for now, at least for natural numbers. And we'll make one note. An important property of exponents, if I take b to the n and then multiply that by b to the m, what should that equal? Well, how many copies of b do I have? This means b times itself n times, and then multiply that by m more copies of b. So b times itself n times, and then times m times. How many copies of b do I have here? I've got n plus m of them. So this is the same as b to the n plus m. And this is perhaps the most important property of exponents, sort of how they interact with each other under multiplication. Well, as long as the bases are the same, you can add the exponents together. So we'll do an example. Just a really quick example. How about 12 or 2y cubed times 6y to the 5th? What is that? Well, of course I've got 2 times 6, so 2 times 6. Let's go with the brackets to indicate the multiplication there. I've got 2 times 6, but then I've got y cubed times y to the 5th, and as we just saw, well, that's y to the 3 plus 5. Right, we add the exponents together. So this simplifies down to just 12y to the 8th. And that's not particularly hard, but it is an important skill because we're going to work with expressions like this all the time, and you have to be comfortable with adding exponents together, multiplying these so-called coefficients together, and so on. so that expression we just had, 12y to the 8th. I want to talk a little bit more about it. 12y to the 8th. What we're going to call an expression like this, we're going to call this a term. All right, so this is called a term. And what makes it a term? Well, it's a combination of a few things here. One is we've got this 12. 12 is the coefficient, but it's just some real number. So I've got some real number, any real number. It's multiplied by y. And y could be any letter at all. All that matters is that I allow it to be variable. So y is the variable. And lastly, that variable is raised to an exponent. And what's important here is what this exponent is. Not the fact that it's an 8, but the fact that it's a natural number. Or I'm going to allow it to be 0 as well. So the exponent must be, how can I say natural number or 0? A shorthand way of saying that, I could call it a positive integer. Or sorry, must be a non-negative. I guess because 0 is not a positive number. So a non-negative integer. Alright, so what I mean by that is 0, 1, 2, 3, and so on. So an expression like this, a coefficient, some real number, times a variable raised to a non-negative integer power, is called a term. And just a little bit more terminology, the degree of a term is equal to the power of its variable. So in this case, our term has degree 8. Right, just the value of the exponent there. So why are we talking about terms? What we really want is polynomials. And a polynomial is just a sum of terms. So it's a sum of a whole bunch of expressions that look like this. A polynomial is a sum of terms. And that's all that a polynomial is. So for example, I'm going to erase this and write down a few examples. Alright, so for example, let's go 5x cubed minus 2x squared plus 1. Each of these individually are terms. Here's 5 times x cubed, so coefficient, real number, times a variable raised to a non-negative integer power. Same thing, this is a term. And 1 is also a term. All constants are terms because I can think of this as being 1 times x to the 0. Right, next to the 0 is just 1 itself. So all constants are terms. So this is a polynomial. How about square root of 2 times z to the 19 plus z to the 11 minus 3z squared? This one looks a little bit scarier because I've got this root 2, but remember, coefficients can be any real number at all that you want. The only real condition is that my powers are these non-negative integers. So this is a sum of terms, this is a polynomial. But for example, something like this, x squared plus x to the 3 halves, this is not a polynomial, right? Both of my coefficients are 1, that's fine. This first expression is in fact a valid term, but my second expression here, I have a fractional power. That's not allowed, right? So this is not a polynomial. Neither would something like this be. How about square root of x plus x to the minus 1? And both of these, let me throw a coefficient in here, 3 plus 3x to the minus 1. both of these break the rules, right? X to the 1/2, you might remember x to the 1/2, or sorry, square root of x. That is technically x to the 1/2. That's what 1/2 powers mean. We haven't talked about it yet. But square root of x breaks the exponentiation rules. And similarly here, nice coefficient 3, but my power of -1 is not allowed. And you might remember x to the -1, that really means 1 over x. But once again, this is not a polynomial. So keep this in mind. Keep this in mind of what a polynomial is. A polynomial is just a sum of terms. And the only real rule is that my powers are non-negative whole numbers, integers. Let's do another exercise here. What are the degrees of all of these terms? Y to the 6th. What's the degree here? Well, that's a term, and y is raised to the 6th power, so it's degree 6. 5y cubed, that's degree, the value of the exponent on y is 3. Minus y, by the way, coefficient here is -1. That's degree 1. And 3, remember what this really means, that's 3 times y to the 0, right? That's how it is a term. So that's degree 0. And what I want you to notice is that every time I've written a polynomial so far, I've written all the terms in order of decreasing degree, right? I've put the highest powers first for a reason. And 1 is it looks nicer, it's easier to read. But 2 is we define the degree of not just the terms of the polynomial, but the degree of the entire polynomial. We define the degree of the entire polynomial to be the degree of the highest degree term that we see. And if I order them in terms of highest degree, then all I have to do is look at the first term, right? So the degree of a polynomial, right? Not just the degree of individual terms. The degree of the polynomial on the whole is the degree of the highest degree term. And if you always write your polynomials in order of decreasing powers, decreasing degrees, then all you have to do is look at the leading term. Look at the first term in the expression, and this will tell me, so in this case, the degree of this polynomial equals 6. Okay, so just to wrap this up a little bit, so far we've really only looked at polynomials in one variable, and that is I've only had one variable in all of my expressions, right? If we either call it x or y or z or whatever. But there are polynomials in more than one variable. So for example, 5x cubed times y squared plus 6x squared plus 3xy plus 1. Notice that the difference here is I have two variables now, but still I'm following the same rules. Still my exponents of each of these variables are nice non-negative whole numbers, right? I don't have any fractions or negative numbers there. So this is an example of a polynomial. Is a polynomial in, how many variables do I have? Just x and y. So in two variables. So x and y in this case. And this will happen from time to time. We'll often have two variables. And all I really want to point out here is how we handle degrees in this case. So this term here, what's the degree? Well, one reasonable way to define this is x is raised to the power 3, y is raised to the power 2, So I'm going to define the degree to be the sum of the exponents. So this has degree 5. And that's exactly how we define degrees when you have multiple variables. You add the powers of all the variables in the expression. So how about this one? 6x squared. You could really think of this as being 6x squared times y to the 0, right? I'm not writing the y expression there because it's raised to the power of 0, but 2 plus 0 is 2. So this has degree 2. What about this one? Well, this is x to the 1 times y to the 1, so that's degree 1 plus 1 equals 2. And lastly, constants. This is x to the 0 times y to the 0, so that's degree 0. And for polynomials in two variables, we define the degree of the entire polynomial to be exactly as we did with one variable. It's the highest degree term that you see. So polynomial degree is equal to 5. Alright, so similarly, you could have polynomials in 3 variables, 4 variables, 5 variables. They'd be very complicated, but just proceeding along these same rules, you can define all those similar types of expressions. The only thing that we require, once again, is that your exponents be non-negative and whole numbers. Oh, and one last little bit of terminology before we actually do some algebra with these things is a monomial. A monomial is a polynomial with exactly one term. So a single term polynomial is a monomial. And I mention this because we talk about binomials all the time. Binomials are extremely common types of polynomials. These are polynomials with exactly 2 terms. And fairly often these pop up as well, trinomials. Obviously you get the naming schemes here. A trinomial is a polynomial with 3 terms. Okay, so last but not least, all we have to do now is talk about how do we add polynomials together, how do we multiply them together. Okay, so we want to add or subtract polynomials, and I won't go too into detail as to how this works because I know you've done this before. So how do you add and subtract polynomials? Well, you just add and subtract like terms. What do I mean by like terms? I mean terms that have exactly the same variables and raised to the same powers. Alright, so same variables to the same powers. And that's probably enough, reminds you of how this works, so all we have to do is probably just teach this by example, I think. So, for example, here's a polynomial. 8x squared plus x plus 3. Don't really need the brackets here, I just want to indicate which 2 polynomials I'm adding together. Plus 3x squared minus 2x minus 1. And if someone was teaching this for the very first time, they might write a few more lines than I'm going to. We've all done this before though, so we'll just jump straight into this. What are my like terms? Well, here I've got a term with an x squared, and here I've got a term with an x squared, so I'm going to add them together. I've got 8x squareds plus 3x squareds. 8 plus 3 is 11, so I've got 11x squareds. What else do I have? I've got x minus 2x, so those are like terms. And 1x minus 2x is minus 1x, so that'll be minus x. And then lastly, I've got my constants are like terms. 3 plus minus 1 is plus 2. Alright, so not much to addition of a polynomial, let's just add the like terms together. We'll do subtraction. Let's do 12y cubed plus y minus 6y squared minus y plus 1. Alright, so I've got 12y cubes over here, and I'm subtracting how many y cubes? 0 y cubes, right? They're technically here, it's just I haven't written them because it's 0 of them, so minus 0 y cubes still leaves me with 12 y cubes. How many y cubed squareds do I have? Well, I've got 0 y squareds minus 6y squareds. So that leaves me with negative 6 y squared. Then I've got y minus y. So how many y's do I have? Minus minus y, minus minus becomes plus, so this is y plus y is plus 2y. And last but not least, I've got 0 minus plus 1. Leaves me with minus 1. So sort of you just have to make sure that you remember that this is really addition, but I'm distributing this negative sign all the way through. So in other words, I'm really thinking this as being plus minus 6y squared, and then minus minus y is plus, and then minus 1 is an equivalent expression. Let's move on to multiplication. How do you multiply polynomials together? Well, you really just use the distributive properties all over the place. So for example, what does it mean to take 6x plus 1 times 2x squared plus x minus 3? And you might be thinking, anytime I multiply polynomials together, I just FOIL, right? You remember this expression FOIL, but a FOIL only works if you have a binomial times a binomial. And here I have a binomial times a trinomial, right? 2 terms and then 3 terms. So I'm not actually FOILing. The way you multiply polynomials together in general is you distribute. So what this really means is the first term, 6x, times this entire polynomial, plus the second term, which is just 1 in this case, times the entire polynomial. And what now? Well, now I distribute again. So what does this mean? This means I take 6x times 2x squared. So 6 times 2 is 12. X times x squared, remember you add the exponents together, so x to the 1 times x squared, 1 plus 2 is 3. So that's 12x cubed. Then we've got 6x times x, so plus 6x squared. Then we've got 6x times minus 3. Minus 3 times 6 is minus 18x. Do the same thing with the other expression, but this one's pretty easy because it's just 1 times all these terms. 1 times 2x squared is 2x squared. 1 times x is plus x. 1 times minus 3 is minus 3. And we're technically done at this point, but you should never leave a polynomial looking like this. You should group all your like terms together. So how many x cubes do I have? Just this expression, 12x cubed. What about x squared? So I've got 6x squared plus 2x squared, so that's plus 8x squared. We've got minus 18x plus x, that leaves me with minus 17x's. And last but not least, we've got the negative 3 term. Awesome. So yeah, that's how you multiply polynomials. You distribute. We'll do 2 more examples though. Alright, so we've got m plus 3n times m minus 2n. So here you might say, well, this is a binomial times a binomial. I can FOIL, and yeah, I'll FOIL in a second, but let's just do this using pure distribution. This means m times m minus 2n plus the second term, 3n times m minus 2n. And so there's distributivity. And now we just have to multiply these out. So m times m is m squared. M times 2n is minus 2mn. Here we've got 3nm. And 3n times 2n is minus 6. 3 times 2 is minus 6. N squared. N times n is n squared. And once again, we should group like terms together. So this is m squared. These 2 terms are really the same. I've just written m and n in opposite orders. But commutativity tells me m times n is the same as n times m. So how many do we have? Minus 2 of them plus 3 is just plus 1. Plus nm. We'll go alphabetically. mn minus 6n squared. By the way, our next section is factoring. Factoring is the opposite. It's the question of, if I have this expression, how do I go backwards? How do I write it as a product of two polynomials like this? So that'll be our next section, A3. Or you could just FOIL this. And to be honest, this is how most people would proceed with a binomial times a binomial, is you do so much of this multiplication of polynomials in practice that you do a lot of it mentally. And remember, foiling says, okay, multiply f for first, multiply the first terms together, m times m is m squared, multiply the outside terms together, so m times minus 2n is minus 2m times n. The inside terms, 3n times m, so plus 3n times m, so I'll write this mn. And then L for last, multiply the last terms together. 3n times minus 2n is minus 6 n squared. And that's of course exactly what we have above, once you group the like terms together. So with binomials, yeah, you can FOIL, no problem. Let's do one more example. And if you haven't cubed anything in a while, this should remind you of how to cube stuff. So if I said 2x minus y squared, you'd probably remember how to square, that's just foiling. How do you cube stuff? Well, what this really means is this is 2x minus y times 2x minus y times 2x minus y. And what I can do is just forget about this first term for a second. So 2x minus y, or forget about that first binomial rather. And here, with these two terms, we'll just FOIL this out. So we'll just handle this multiplication separately. Alright, so foiling this really quickly, we've got 2x times 2x is 4x squared. Then we've got the outside terms, 2x times minus y is minus 2xy. Here we've got minus y times 2x is minus 2xy. And then minus y times minus y is plus y squared. No real reason to go to square brackets here, I'm just doing this stylistically, I guess. But I want to group these two terms in the middle together. So we'll go 4x squared minus 4xy plus y squared. And now, just by sort of ignoring this first term for a second and handling these two binomials, now I've reduced this from a product of 3 polynomials to a product of 2 polynomials. And now we know how to handle products of 2 polynomials, right? That's all we do. So now what does this mean? This means 2x. We'll do this all mentally. So what do I have? I've got 2x times 4x squared is 8x cubed. Then we've got 2x times minus 4xy is minus 8. How many x's do I have? X times x is x squared, and a y term. And then 2x plus y squared is plus 2xy squared. Alright, so that's 2x times the whole polynomial. Now we've got to do minus y times the whole polynomial. So minus 4x squared y. We've got minus y times minus 4xy is minus minus becomes plus. This is plus 4x y squared. And last but not least, minus y times y squared is minus y cubed. Now I'm just going to look for like terms. We'll group the like terms together. 8x cubed, of course, stands alone. Here I have an x squared y and an x squared y. I've got minus 8 of them and minus 4 of them. That's minus 12 total. Then I've got an xy squared. I've got plus 2 and plus 4. So plus 6 of those total. And I think that took care of all the terms except for this one, minus y cubed. And there's the this expression cubed. Right, so just to recap, if you cube it, what does this mean? This means the expression 2x minus y times itself 3 times. But we only handle one polynomial times another polynomial at most. So just take two of them, those two that I chose to go with here, and multiply them together sort of on its own, right? Just handle the multiplication of two polynomials at a time. And when you multiply these together, that becomes a single big polynomial. And then I can multiply it by this guy. So if this was raised to the power of 4, you would just do this process over and over again. But yeah, that wraps up the section, I think. Thanks.